Learning Measure TV, a science and engineering podcast with emphasis on measurement, brought to you by David Archer and LearningMeasure.com. Episode 21, Introduction to Vectors. Hello, I'm David Archer. I'm the owner of LearningMeasure.com and LearningMeasure.tv. This is our little podcast. First, a little bit of news from LearningMeasure.com. LearningMeasure.com is a subscription-based training website associated with this podcast. When you register as a student, you get 2 free weeks of access into all the courses. And then after that, if you want to stay take the rest of our courses, it's $5 a month. I'd like to announce 2 new courses that were just added to the course catalog. Math 50, Applied Math for Calibration Technicians, and Math 51, Applied Statistics for Calibration Technicians. These are the first 2 courses in a 3-part course that cover the 3-part series that covers the Applied Math and Statistics portion of the ASQ Certified Calibration Technician exam. Many of the courses that we have on LearningMeasure.com are associated with what is required knowledge for the ASQ Certified Calibration Technician exam. So what we've decided to do is create a new feature on LearningMeasure.com called Programs. In Programs, programs are groupings of courses that you can sign up all at once that are related to a specific topic. Our first program we created was our ASQ CCT exam preparation program, where we've grouped all the courses that we currently have that are associated with the ASQ CCT exam body of knowledge. We are hoping to add to that as we add more courses that are related to that. So now, instead of having to pick through them, you can just click on one button, sign up for all the related courses. We're going to be adding more programs in the future, grouping courses together that have common topics or go towards a common certification. So look for that expanding as time goes on. And tell us what you think about that feature. Okay, the topic of this episode is vectors. And I want to emphasize I'm doing a little thing where I'm trying to do 3 in a row that are related in some way that may not be clear. But this week we're going to talk about vectors. What is a vector? Well, vector is a quantity that has a magnitude and direction. They're usually sort of depicted as arrows. Magnitude's associated with its length, and obviously the direction is associated with direction it's pointing. Well, what can you do with a vector? Well, I should ask, there's a lot of quantities that you might measure that are vectors. An example is an electric field. Well, a field is something that's just associated with points in space. So a set of vectors where each point in space has its own vector attached to it is called a vector field. Examples of that are electric fields, gravitational fields, possibly flow fields in liquids. But there are vector quantities. Example of things that aren't vectors, there's scalars like temperature. A temperature at each point in the space is a scalar field. One particular component of a vector may form a scalar field. Okay, so there are actually real quantities that are vectors that you can measure. What can you do with them? Well, let's say you have 2 vectors, A and B. Let's call this one B. Okay. Property of vectors is they have magnitude and direction. So you could put the arrow here, put the arrow here, put the arrow here. It still has the same magnitude and direction. It still has the same length. It's still pointing in the same way. So you can move these things around, and they're still the same vector. Okay, because all you're concerned about is the magnitude and the direction. Now the magnitude and direction may be associated with a point in space, if it was a vector field, but the vector itself, you can move it around and it doesn't matter. So what can you do with them? Well, let's try adding them. How do you do a plus b? Oh, I forgot to mention, this is a typical notation for vectors when you're writing a letter with an arrow over it. There's all kinds, you might see all kinds of variations on this, you know, single lines, a squiggle underneath, but this is the one I like, okay? In textbooks, generally a vector is written in boldface type with no arrows, generally. Okay, what is a plus b? Well, the rule for adding two vectors is you take the first one, slide this over here so it's at the tip of the other one. It's still the same vector. It still has a magnitude and a direction. Okay. And then you look at, from the tail of the first to the head of the second is a plus b. Okay, now we know how to add vectors. Okay. Well, what else can you do with a vector? Well, you can multiply it by a number. You have some vector A. It has some length. Well, you can multiply it by some number A. So that would be a vector that's A times larger than this. So it just stretches it. Multiplying by a number will stretch a vector. In particular, you can multiply a vector, let's say vector B. Say this is vector B. You can multiply it in particular by -1. Well, what does that do? Well, that flips the direction of the vector. Okay. Same length pointing in the opposite direction. Well, what if we do that? We take this, we slide this up here. I try to make it as parallel as possible. And this is minus b. So this is a plus minus b. Or we can call that a minus b. Okay, we just defined subtraction of vectors. You flip one around and you slide them and you do the little geometric things we did before. There's another way to do it, but we won't go over that real quick right now. What else can you do with vectors? Well, you can take linear combinations of vectors. A vector of the form a times a plus b times b, okay, vector scalars, okay, these are numbers, these are vectors, okay. This is called a linear combination. So linear combination. Okay, so any vector of the form, of this form, is a linear combination of two vectors. The total, all possible linear combinations of 2, 3, 4, however many vectors, is called the span of those vectors. So the span of A and B for two vectors, this is the sum, is all possible combinations of this form of those two vectors. If the span covers the whole space you're interested in, it's called, those vectors are said to form a basis for the space. So a basis is is a set of vectors whose linear combination completely covers every possible vector in the space you're interested in. The minimum number of basis vectors required to span a space is called the dimension of the space. Okay, these are all concepts with vectors. So the number of vectors, the minimum number of vectors it takes to span a particular space is called the dimension of that space. In a two-dimensional space like this whiteboard, you only need two vectors to specify every point on the whiteboard, I should say. Okay, that's the concept of dimension. So when you talk about 2D space, it means you need two things to specify everything in that space. Generally, we live in a 3D world, so you need three vectors to specify all points in space. So your basis has three vectors in it. Those are all concepts associated with vectors. Well, there's another one called the dot product. Dot product. Oh, before I do that, there's a notation here. That means the magnitude of A. That gives you the length of that arrow for that vector. So there's something called the dot product, which A dot B is equal to magnitude of A times the magnitude of B times the cosine of the angle between them. So if you have two vectors, A and B, with the angle theta apart, this is the dot product. And you can see from this, this is also equal to B dot A. It doesn't matter what order you do it in. See, that's going to be the same. This is the same because this is the definition. So it's the length of one times the length of other times the cosine of the angle between them. Well, there's a special case. If they're parallel, especially if they're the same vector, okay, that's the maximum value this is ever going to get. So this is one vector. Well, let's say, what is B cosine theta? Well, if you do a little geometry, this B cosine theta part here is the projection onto the first vector of its length, of this vector onto there. There's a right angle here. You could also group these two together, so it's the magnitude of B times the projection of A onto B. Projection just means as you drop a right angle, and so how much of this vector is along this vector. That's a projection. Okay, there's another special case. There's a special case. Well, when cosine theta is 0, A dot B equals 0. Well, for when this case is true, the vectors are said to be orthogonal. Okay. Now, in the particular case, if A is non-zero and B is not 0, it means they're perpendicular because cosine theta is 0. So theta has to be 90 degrees, so the vectors are perpendicular. Well, that means, well, there's all kinds of things that are nice about orthogonal vectors in a basis. One is there's no ambiguity of how much of it is a projection on one or projection on the other. That's important, but not what I want to talk about here. But the other thing you can do, if you have a vector and you wanted to form, if you have orthogonal basis, let's say you have a vector like this and one like this. Okay, that's not a very convenient basis because these units and these units are going to be different. So what you probably want to do is normalize each of your basis vectors so that they have a unit vector in this direction, a unit vector in this one. A unit vector is a vector of length 1. Well, how do you do that? Let's say you have two vectors A and B that are orthogonal. That is, A dot B equals 0. And, well, what's the length of A? Well, we can do some things with Pythagorean theorem, but it turns out, and this is how you prove it, that the length of A is equal to the square root of A dot A. Well, is that true? Well, yeah. So the length of A times the length of A, or A squared. So square root would be the length of A. So the vectors A over the square root of A dot A and B over the square root of B dot B are called unit vectors. They form an orthonormal basis. This one's just an orthogonal basis, which means they're basis vectors at right angles. This is an orthonormal basis. It means that each of the unit vectors are 1. Well, what can you do with that? Well, you may have seen before some sort of graph. And we'll call this x and y. Well, if we have a unit vector in this direction, we'll call it x hat. That's the way you sometimes see it written, with a caret over it. And we'll call this y hat. So we have a vector now. Let's say any arbitrary vector x is going to be a times x hat plus b times y hat in 2 dimensions. Okay, and these numbers a and b are called the coordinates of the vector in that basis. So if you have a point here, a and b, and a vector, okay, so that's, and this is x. Well, we now have essentially, you've seen all this before in graphing functions. These are coordinates. So what is the dot product in coordinates? Now we can go through the geometry, but I'm just going to give you the results that you can prove that if you have a vector x and a vector, let's say y, with coordinates, let's say y equals c x hat plus d y hat. Okay, well, what is their dot product? Well, I'm not going to prove it, but it's easy enough from the geometry. You need to apply Pythagorean theorem a few times. But x dot y is actually equal to, in this basis, in our orthonormal basis, where these are the coordinates, it's going to be AC plus BD. That's that is, in this coordinate system, that's what the dot product is. And this is equal to magnitude of x times the magnitude of y times cosine theta. Well, what can you do with that? Well, if you know the coordinates in a basis, in an orthonormal basis, you can use this and this to determine the angle between the vectors. You simply divide this by this and this, and in this basis, what is the magnitude of x? Well, this is a and b. This is a normal thing. This is very simple this. Pythagorean theorem, right? Magnitude of y equals this, c squared plus d squared, square root of c squared plus d squared. We have this, we have those. We can figure out the angle between any two vectors just by looking at their coordinates in a particular basis. Now the dot product is a special case of what's called an inner product. And an inner product has the property that, well, there are several properties, one of which is that, A dot A is greater than equal to 0, and it's equal to 0 only if A equals 0, the 0 vector, which means a vector whose all its components are 0. And it has to have the property A dot B for any two vectors is less than or equal to A magnitude of A times the magnitude of B. And so on. I'm not going to list them all, but let's go on to a different thing. Now we have, we've done all this in 2 dimensions. Let's go to higher dimensions. Well, in 3 dimensions, normally you would add another unit vector like CZ hat, where Z hat is a unit vector in the Z direction. 4 dimensions, it gets harder. But let's, instead of going to 4 dimensions, let's go to n dimensions right off the bat. Let's say we make ourselves somehow an orthonormal basis in n dimensions. Now we've gone beyond the point where we can visualize vectors as arrows, although there still would be arrows in that dimension. But now we basically have to write it all algebraically because our minds start going weird at higher than 3 dimensions. So we'll define an orthonormal basis where the basis vectors are unit vectors, and we'll label them with an index, and we'll say the EI are unit vectors in this n-dimensional space. Well, a vector x is going to be written as the sum I equals, let's say, 1 to n of some coordinate ai, well, let's say xi, times ei, unit vector. Okay, and y, let's say another vector in that space is going to be I equals 1 to n of yi, ei. Well, think about last week. Think about what this is starting to look like. Okay, we've got this high dimensional space. What's length of x? Well, Pythagorean theorem still works in n dimensions. So it's the square root of the sum of I equals 1 to n of xi squared. So you just sum up all the squares of the component, takes the square root. That gives you the length of the vector in that space. Same thing for the magnitude of y. Square root of yi squared. Well, what's the dot product in this n-dimensional space where n is greater than 3? Well, well, you can show that this is, let's see, x dot y in n dimensions is going to be the sum of n, or I equals 1 to n of xi yi. But hey, this is equal to, still, by definition, magnitude of x, magnitude of y, times the cosine of the angle between them. So we now, by defining things this way, we can look at the angle between 2 vectors in any number of dimensions. Kind of cool. But, what if we did something like this, or x dot y And let's say the coordinates were some sorts of functions. Let's say this one was I equals 1 to n. Let's say that this particular function was, each of the coordinates was something like e to the I omega I t, let's say. Each one of the coordinates in this n-dimensional space was some sort of function that looks like that. I mean, you could think about in 2 space. I mean, you could have a vector in 2 space, cosine t x hat plus, y sine, y sine t y hat. I mean, that's a perfectly legitimate vector. It's just something that's a function of time. And let's say this is the coordinates here are some sort of f of t. And then let's multiply both sides by something. Okay. And leave it at that for this week, and we'll talk about what that's going to mean next week. Okay. Or next time, whatever, maybe not next week, because I don't know how often I'm going to get these off this year. But anyway, we're talking now, the idea we're going to get to is functions can be sort of thought of as vectors in some sort of infinite dimensional function space. And you can do inner products of functions with basis functions that we can actually form things like orthonormal basis in function space. These are some sort of bizarre, where n is now, instead of being finite, it's infinite. But it's conceptually, it's no different than the vectors in 2, 3, n space. They are just, it is exactly what we're talking about here. You're getting components of functions in terms of other functions, which we'll call basis functions. And you define something called an inner product, which is like a dot product, which is actually exactly a dot product in infinite space, infinite dimensional space. In this particular case, for the function space, the number of basis vectors you need is infinite. There's no finite amount of vectors. You can approximate a function with a finite number of vectors, and we'll talk about that too. All right, this is going somewhere. Maybe it's not obvious where I'm going. Some of you, it's probably caught on where I'm going with this already. But anyway, that's all I wanted to talk about this time. Next time, next time we're going to do a little bit more. Okay, if any of you have any questions that you want answered, engineering related, science related, homework related, doesn't matter what, send us a question at question@learningmeasure.tv. We really want your questions. If you have any suggestions for a topic to cover or somebody to interview or something, or send us an email at suggestions@learningmeasure.tv. And if you're a vendor of services or want to be on the show to give a talk on something, let us know. Send us an email at vendors@learningmeasure.tv. That's it for this time. We'll see you next time.